On with Tectonics video number 2. And in this video, I'm going to try to keep them short so that you can do them in, more often during the week, but at shorter time periods. So I'm going to try to keep them down to 10 to 15 minutes. In this video, we should cover some of the stuff about boundaries, but we're not going to cover specifically boundaries because we did that in the last video. What we're going to be covering is what makes up boundaries, which are faults. Now, in class, we did a bit of a recap. If you weren't in class, you might want to go over these questions, push pause and look at them, and you might want to cover these questions as well. Now, in class, this part of your notes, we actually drew in class together, or we will draw in the next class period. So in your notes, go ahead and skip that page. We will come back to it next time, next class period when we were together. All right, so earthquakes. Earthquakes are basically vibrations or waves that move throughout the entirety of the planet. They result from rock fracturing in the lithosphere. So basically what we have here is fracturing of rock due to tension stress, which would be pulling apart, compressional forces, pushing rock together, and shear stresses sliding past. When rock breaks, it sends waves through the body of the entire planet and along the surface. Now remember, as you're taking notes, pause when you need more time to write. All right, now when we're talking about earthquakes and we're talking about the tension stress where it's pulling apart, compressional forces where it's pushing together, and shear forces, you might be thinking about boundaries. And you might be thinking, okay, well, tension stress where it's pulling apart, that's got to be a divergent boundary. Or compressional forces, that's got to be a convergent boundary. And shear stress, well, that's got to be a transform boundary. Yes and no, because earthquakes can happen anywhere. They happen here in Utah. We've got a fault line. I don't know if you grew up in a cave and you didn't hear about this before, but there is the Wasatch Fault, of which we live upon. And these forces don't have to be acting in a certain boundary. Now think of an entire plate. One edge of the plate may be at a convergent boundary. One part of the plate might be at a transform boundary. For example, the North American plate. We are in the middle. Well, let's pretend we're in the middle of our plate. Out in the Atlantic Ocean, there's a spreading center. There's seafloor spreading going on. There's a divergent boundary, which is pushing our plate apart from the Eurasian plate. Now, if you think about that, that would be pushing Utah to the west. However, our boundary in California is going to a side-to-side because it's a transform fault. That movement is going north and south. So all the rock everywhere in the middle is going to have these different forces put on them. Some places it's going to be pushing, sometimes it's going to be kind of torquing, sometimes it's going to be pulling apart. And it doesn't necessarily have to be at plate boundaries. So earthquakes can happen everywhere, but they do happen much more frequently and much more often where those plates come together. All right, so a focus, we're going to draw this in our notes, but the focus, write this down first, is the fracture point in the crust. Now, don't draw this just yet. We'll draw it in a minute. But right here, so this is an example of what we call block diagram. Basically, we're looking at the surface of the Earth, and we've cut the Earth and sort of pulled it out so that we can see what we might see if we can see inside the Earth. So the focus, this is the place where the rock has actually broken. The fault here, the fault is the line of which, or the plane at which that breaks. Sorry, I skipped ahead. Epicenter. Epicenter is a location directly above from the focus. Fault. So the fault, sorry, let's go back. Let's go ahead and enter this diagram in. So what you're going to want to do is when you're creating a diagram like this, is the easiest thing to do is make your outline of your box. So let's say here they had a little bit of water, but that's all right. We don't have to have water there. And then they had a definite fault that was weathered and eroded. And then they had this here. Now we're going to draw two parallel lines, the same distance going back into our paper. We're going to connect those two parallel lines with a straight line down, the straight lines. And we're going to mimic the same surface here. But first I'm going to draw a line that's parallel to that. And then the same line, I'm just going to carry out that same line that I did in the back of my frame. Alright. Now, in our picture, I actually had a line here. Let's go ahead and label that the fault. And it had the location of where the earthquake occurred inside the earth. That was our focus. And then directly above on the surface, that was our epicenter. Now the earthquake occurs here, and then we have a movement of waves that move up, and it's going to spread, and they'll keep trying to draw the sides. They'll keep spreading throughout the entire earth. Now, as that energy, because of waves energy, moves through the earth, eventually it will become absorbed, and it'll be absorbed different ways inside the earth. Okay, now we're back to our diagram that we had on our paper there. Now, if you notice, this thing here, we actually didn't put this in our notes, but this is called a fault scarp, which is kind of weird and kind of strange. And what we have is we have the fault going this way, but our scarp seems to be falling this way. This is obviously an old scarp because it's been weathered and eroded down to curved in this manner. But if this was a fresh fault scarp, if this happened at this earthquake, we would actually see it follow a line here and be built out this way. And the cliff face would actually be overhanging the ground. Now, fault. Faults are places where rock gives way due to crustal forces. Many faults make up a plate boundary. So a plate boundary, where the plates come together, are just made up of many, many different faults put together. It's not one long fault. It's many, many, many. The longer the fault, the larger the earthquake could be. So if an entire plate boundary was one fault line, every time we had an earthquake, we'd pretty much just die, probably. All right, so fault types. We got 3 different fault types. There's actually technically more, but 3 that we need to know. So a strike slip fault. This is going to be our transform boundary. Diagram's going to look a lot like the transformed boundary diagram. This is where it slides past one another. We've got the normal fault, where we've got pulling tensions, pulling rock apart, so one will slide down. It separates the rock through that motion. And then we have a reverse fault, where it's compressional forces. Forces are pushing together, and it causes a slip of the rock, and one rock will move up. That diagram we just drew of the focus, the fault line, fault plane, and the epicenter, that was an example of a reverse fault. All right. Here are a bunch of diagrams of our different faults. Now I'm going to draw these for you, so if you're like kind of going crazy trying to figure out how to draw these, it's okay. I know a lot of people struggle with drawing 3D diagrams. So here, it's not letting me zoom in. Here we've got what it might look like if the ground was not ruptured, if it didn't break. Now here we've got an example of a normal fault. We've got the fault plane. We've got this wall sort of leaning backwards. Yeah, this wall looks like it's kind of overhanging. And then we have some faulting. We're going to draw this one, but almost never in a strike slip fault do you have just 2 blocks moving perfectly side by side. A lot of the times you'll have one side sort of moving up while they move side to side, or you'll have one kind of overtaking the other. They kind of grind into each other. They almost never just go nicely, perfectly, and just slide side by side. But it does happen. All right, the first one we're going to draw is a normal fault. We call them normal faults, not because they're the most common, but actually I think they are the most common. But we call them a normal fault because that's what we were used to. And then we discovered that it was a different kind of fault, and we were like, oh, well, then these are going to be the normal ones. And then since the other one's the exact opposite, we decided to call that one the reverse fault. So we're going to start with the normal fault. Now, I'm going to go ahead and draw myself a line here. And this line is going to carry out this straight. And I'm going to go ahead and draw the top of my block here. Now this one should be a little bit longer than my first one, because I'm going to draw my fault plane leading down to that one. Now on this, I'm going to try to indicate different rock layers by drawing lines and just kind of giving them different symbols. Now if you have colored pencils and stuff, maybe those will work better for you. Go ahead and draw some rock layers. Maybe we have some limestone like we have out on our mountains, the Wasatch Fault here. Maybe we've got some sandstone or some quartzite covering that as well. Not that this is a symbol for quartzite, I'm just making up stuff. And then maybe we've got some topsoil up here. And some plants. Yay, plants. All right, so what we have here, if this was a ground surface and the earthquake hadn't happened yet, don't draw this. My ground surface might be here. I'm going to draw it in pencil here. It might be just right here on my block diagram. It would look something like this. I'd have my rock here, my rock here, my rock here, and these would match up just perfectly fine. Earthquake happens. We've got that pulling force. So this block is sort of moving this way. This block is moving this way. We've got these forces, these tensile forces pulling apart. So what we have is this whole entire block, or this section, imagine this is an actual spheric plate that moves on, gets pulled away. And so as it does that, we can see something that might look like this. This is what you should draw in. So this whole block gets moved downward. And so we end up having, this is our topsoil, you got our plants up here. And then we have this layer and this layer. Now, whatever you're drawing for this layer, it should be the layer that was up here. So this layer here that's dropped down, what I pretended to be limestone will be there, and then this rock will be here. So basically what we have is we have two sections of rock, one that has sort of dropped down. So this surface creating a fault scarp here. And I'm going to label that because I don't think we have that anywhere in our notes. So if you see that written somewhere, you can understand what that means. Now, we could make this 3D. If you don't want to make it 3D because it makes you confused, I'm just going to draw parallel lines. They're going to be the same distance in 4 different locations. So that was parallel, 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 parallel. And I'm going to make my surface like that. This line I'm going to mimic right over here till it meets my land surface. Going to add another parallel line in there. And then I'm just going to connect my corners. And now I have a 3D drawing. Well, that wasn't a very good straight line, was it? All right, let's go ahead and draw ourselves a reverse fault. And let's see how that would look in the opposite or reverse way. All right, so the reverse fault here, go ahead and reverse fault. We're going to have sort of the same thing where we have one side that's going to have a fault. Go back on this one and enter your fault plane here. I forgot to write that in there. It's probably very important. Anyway, so we've got this, and we're just going to basically have an opposite condition of what we have here. So I'm going to draw this first block first. And I'm going to draw a straight line down here, and I'm just going to connect to this line here. Now I'm going to have maybe my topsoil here. I'm going to have my I'm going to use the same pattern. You don't have to use the same pattern, but I'm going to use the same pattern as the last one. I've got my limestones here. I've got maybe, I don't know, we called this sandstone last time. I don't even know what we called it. All right, so now I'm going to, again, don't draw this. I'm going to pencil in this next section. So we've got our land surface here. So this is maybe my other side of my lithospheric plate. And what's happening here is we've got forces, compressional forces now. If you want, you might want to put compressional forces, pushing the two rocks together. Now in this plane, instead of dropping one down, this block is going to push up. So we're going to push them together, and it's going to cause one block or the other to push up. Probably should have drawn this better. Should have drawn the other side first. But this one is actually the one that's going to go up. And we're going to get an overhang of this ledge here. So to draw that, I'm actually going to put this one down. Probably should not have done it that way, but that's the way I did. So that's the way I'm going to have to do it. I'm just going to go ahead and finish my block here. Now I'm going to copy the same rock formation so I can understand that this has dropped. And then I've got this here. I'm going to erase my pencil line in case that's confusing anybody. All right, so here, now we've got a fault scarp here. And notice this overhanging. Eventually, weathering erosion will weather this down, and then it will be sort of a curved fault scarp in that direction. Now to make it 3D, I'm going to take some parallel lines. So 1, 2, 3, 4, 5 parallel lines. And then I'm just going to connect my corners. All right, now remember this here is our fault plane. All right, and I think I have used up more than my time on this one, 17 minutes. So I'm going to go ahead and pause the video, and we'll do the transform faults and the rest of plate tectonics on the next video.